lecturer, as I said, at QUT, and currently a DECRA fellow, which is the world's saddest time to have a DECRA because we can't go anywhere or do anything interesting. And it's been really awesome to hear everyone's talks. Like, if I was the ARC and the ARC knew how awesome everyone here was, I think no one else would ever get a leg in for any amount of money from the ARC. So it's been really awesome to have a chance to hear about everyone's work. So here at QUT, I co-lead little domains and themes in the Centers for Data Science and Center for the Environment. And that really speaks to my research, which sits, I'm a mathematician, but my research really sits in the application field of ecology and biodiversity conservation. And so particularly what I look at in my work is ecological decision science. And this is the idea of using decision science ideas and techniques from mathematics, so thinking about optimization and OR kinds of approaches to answer questions about the environment and protection of the environment. So when we're thinking about saving species and ecosystems, we have limited time and money and personnel, and we have a lot of endangered species, ecosystems, and processes. We, as a society, need to get a lot out of the environment. So we need food and land and water and recreation and storm protection and a ton of what we call ecosystem services out of the environment. And so we're kind of looking at this balancing act of only having limited resources to protect and manage the system, but this really critical need and multiple objectives for why we need to protect these systems. And of course, when we as mathematicians see difficult decisions in complex systems, of course, that leads us to think about operations research, decision science, and optimization for making those hard decisions. So making decisions in ecosystems is a particularly difficult context to make these types of decisions because it's a really complex system. So in ecosystems, so an ecosystem is like the species in an environmental system plus the environment plus maybe how we interact with it. So there's a lot of really complex interactions there between individual animals, between species. Those things depend on age and distribution and all of these complicated things. There's a rapidly changing environment. So not only is the system itself changing, but we're looking at rapidly changing for example, because of climate change types of reasons. We have humans interacting with these systems so they can help or they can hurt. And that like helping or hurting piece can be really unpredictable, adding complexity. We tend to have patchy or poor data of most environmental systems. In some places we have excellent data because people are really obsessed with those species, but in other places we have really poor data. And we mostly can't test our management. So we can't do experiments of these things and see what happens because, you know, one of the most classic examples of testing management was releasing cane toads in Australia to deal with the cane beetle. And once you've let it out, then you're in this catastrophic situation. And so it turns into a really complex decision-making context where maths can come in, or my group can come in with these mathematical approaches and really try and model these complex systems to the end of trying to guide optimal management of them. So I'm going to talk about just a couple of different themes that I and my group tackle here at QUT. So first of all, we look at planning spatial management in the context of people. So the spatial management piece talks about optimal placement, for example, of protected areas, invasive species management or restoration. But we add this layer of complexity to this problem by thinking about the fact that people use those spaces too. So we might want to put protected areas somewhere. The optimal solution might be to put a protected area somewhere. But if people are continuing extractive processes from those places, then we need to think about what that means for either eroding or improving the benefits that we might expect to see for the species and for the ecosystems. And so what that means is we need to layer on, so we need to do spatial and sequential optimization of these systems, of management of these systems. But we need to layer kind of agent-based and economic models on top of that optimization to question, like, how might people be making this a more complex situation? The next kind of little chunk of work that we think about here is thinking about designing policy. So designing policy as in what can the government actually come in, what rules and regulations, policies and incentives and laws might the government be able to come in with? Because really we might think about optimization as you can do an optimal solution, but it's often a kind of a blunter instrument that policymakers actually have. And so it can be really complex thinking about what is it to model those blunter instruments in these complex systems with enough kind of accuracy to then be able to make these optimal decisions in these systems. So we look at, of course, thinking about modeling these systems and looking at multi-objective optimization. Game theory can become really important here when thinking about how incentives might play out, financial incentives or economic incentives. And we've used Bayesian belief network models to understand and design the impact of policies, because once we understand the impact, that's when we can start thinking about managing the impact or optimizing those policies. I wanted to plug this area of research because I'm going to be advertising a postdoc position in the next couple of weeks or next few weeks for this. And so it'd be really great if anyone knows anyone who might be really good for this postdoc position. What we're looking at is this idea of value of information. So we hear a lot about the idea of optimal monitoring, but we're usually saying, how do we monitor systems so that we can refine parameter estimates? How can we be like more sure about the models and functions that we've fit to try and represent an environmental system or any system? But what I'm interested in this value of information analysis is not to refine the parameter estimates, not to be like more sure about those equations, but to refine the optimal management decisions. So refining that parameter estimate is only useful in my work if you make a better decision at the end. And so if that extra certainty can flip you into a different management regime. And so what this looks like is kind of, again, with this layering system, we think about the layering of these spatial or sequential optimization problems, and then layering a Bayesian updating layer on top of that to say, okay, what does it mean to have more information, and how might we be doing two levels of optimization? We're optimizing the actual management, but then we're also optimizing the information that we might be drawing from these different monitoring techniques and technologies. Just on the topic of technologies, another thing that we look at here, and this is what my current DECRA is about, is looking at prioritizing technology development in these environmental systems. So essentially we can optimize and allocate these limited resources until we're blue in the face and think that we're making these best possible actions in these systems. But somewhere like the Great Barrier Reef, no matter how well we act with our current approaches and the technologies available to us, the management options, it simply isn't in many cases going to be enough to be able to save these systems. And so there's a lot of focus, much more broadly than mathematics, in all different engineering fields and tech fields. There's this idea of developing new technologies to do what we can't currently do in these complex ecosystems. But every time you're trying to develop a new technology, you've got really long wait times, really uncertain outcomes, and the potential for catastrophic failure. Either by the time it's ready, the system's collapsed, or you just were completely wrong about how the technology might have helped. Maybe it actually hinders. And so there's this opportunity for mathematics to come in here and make these decisions about optimal allocation of those resources to the new technologies. And how I'm modeling this is it kind of comes out to be a bi-level programming problem, again, with the layers. So there's the layer where if we had the technology, what might we be doing in the system? And then the layer of like, in that context, with that future optimization in mind, how do we make those kind of top level decisions about the allocation of those resources? And the next thing, the last one I'll talk about is a really big focus of mine at the moment, because we've just started our new ARC Special Research Initiative on securing Antarctica's environmental future. And there's nodes of this centre at QUT, at Monash, at University of Wollongong, a bunch of different a bunch of different places, universities and research institutions around Australia. And what we're really focused on is how we can use cutting edge data and technologies and mathematical optimization to really look at securing Antarctica's environmental futures far into the future. And this is because Antarctica is a particularly complex and difficult place to think about modeling and understanding and getting data for. All of the things that I said before are even worse in Antarctica because it's so hard to get there and so hard to get data there. And it's, of course, it's really rapidly changing. And so a lot of the
sorry, Kate, you have minus 1 minute left.
Minus 1 minute left. Good. And so there's a bunch of tools that we're going to use for that. And luckily, that's my last one. Thank you very much.
Thank you. Great.